Okay, we start. Hello, everyone. Welcome to rendering session of IEEE VR 2022. I'm Lili Wang from Beihang University, Beijing, China. Today, we have a 6 wonderful paper in this session. We will first give the presentations of these 6 papers, and after all presentations, we have 20 minutes for Q&A. If you have some question about the paper, please paste them on Discord. So let's start. The first paper is SivsFormer Parallax-Aware transformers for single image-based view synthesis. The speaker is Zhang Chunlan.
Okay. Can you see the screen?
Yes. Go ahead.
Okay. Wait a minute. Hello, everyone. My name is Zhang Chunlan. I come from Beijing Jiadong University. It's a pleasure to present our work in child SivsFormer, Parallax-Aware transformers for single image-based view synthesis.
春兰有点
没办法放映。
Okay.
I'm sorry.
Okay, go ahead.
I'm sorry. Wait a minute. Single image-based view synthesis aims to generate another view from a single input view. This task is challenging as it requires inferring contents beyond what is immediately visible. This technique has been widely applied in virtual reality, 3D, and volumetric display, image editing, and other fields. Previous method directly predicts the unknown views using the convolutional neural network. Wait a minute, I can, sorry. I play the video.
Would you like me to stream the video?
Yes, I think we should play the video. So Chunlan, yeah.
Chunlan, you need to mute yourself.
I'm sorry. I have
Hello everyone. My name is Zhang Chunlan. I come from Beijing Jiadong University. It is a pleasure to present our work entitled SivsFormer Parallax-Aware transformers for single image-based view synthesis. Single image-based view synthesis aims to generate another view from a single input view. This task is challenging as it requires inferring contents beyond what is immediately visible. This technique has been widely applied in virtual reality, 3D and volumetric display, image editing, and other fields. Previous methods directly predict the unknown views using the convolutional neural networks, but the generated views suffer from visually unpleasant holes, deformations, and artifacts. These methods did not consider the view synthesis characteristics effectively. The disclosed regions are invisible background objects in the original viewpoints, but they become visible in the target viewpoint. In other words, the disclosed regions should be filled with background contents. In this paper, we propose a single image-based view synthesis transformer named SivsFormer for high-quality and realistic view synthesis, considering that it is significantly more difficult to generate foreground objects than to synthesize background objects due to the parallax. We designed a warping and occlusion handling module to generate an initial target image to reduce the effect of parallax. And we designed a vision transformer-based disparity alignment module to capture the long-range information over the scene and ensure that pixels move in geometrically correct manner with soft probabilistic disparity maps. In the disparity alignment module, we propose an end-to-end pyramid vision transformer deep network that takes 2D images as input and outputs stereoscopic images. This network does not require the ground truth or depth map as supervision. The whole framework consists of 5 stages, 2 randomly initialized fully connected layers, 6 deconvolutional layers, 1 convolution and softmax layer, 1 bilinear interpolation, and 1 disparity selection layer. Besides, we designed a Parallax-Aware loss function to urge the quantity of the sensitive images to be better and more realistic by aesthetically quantifying the magnitude of the parallax. We perform an extensive ablation studies to verify the effectiveness of each component. The component we added can improve the performance of the algorithm more effectively compared with the baseline. Besides, we show many comparison results. Our approach achieves superior performance in both quantitative and qualitative evaluations. The quantitative results show that our approach can synthesize more realistic images with fewer distortions and artifacts on KT datasets. The experimental results on cityscape datasets are consistent with the KT datasets. In summary, firstly, we propose an overall framework for single image-based view synthesis. Secondly, we present the SivsFormer with the effective multi-head self-attention mechanism. Thirdly, we design a Parallax-Aware loss function. That's all, thank you.
Okay, thanks Chunlan's presentation. The second one is reconstructing 3D virtual face with eye gaze from a single image. The speaker is Liang Jiadong. Jiadong, please. Jiadong, open your audio. You didn't, you mute.
Sorry. Sorry for that.
Okay, please
Okay.
share your screen again.
Okay. Can you hear me?
Yes, I can.
Okay. I'm sorry for that. Hello everyone. I'm Liang Jiadong. My supervisor is Professor Lu Feng. I'm going to introduce our work reconstructing 3D virtual face with eye gaze from a single image. In this paper, we present an advanced 3D face reconstruction framework for virtual reality. Our method takes a single image as input and could reconstruct the 3D face with precise eye region. Based on the reconstructed result, we propose an automatic face rotation algorithm, which can be used for eye contact and gaze interaction. We first obtained the coarse-grained virtual 3D face reconstruction by using the 3D face model. Then we perform shape adjustment and eye texture alignment to achieve the virtual 3D face reconstruction with precise eye regions. Next, the generated 3D virtual face is fed into our eye contact discriminator, which aims to calculate the deviation between the eye gaze direction and the eye contact direction. The discriminator generates the gradient of the deviation as guidance for 3D face rotation. Finally, we specifically design a gradient searching algorithm to find the best rotation angle and makes the virtual 3D face achieve eye contact. To obtain the 3D virtual face from a single image, we employed a 3D based model to get the coarse-grained 3D face. Specifically, a pre-trained CNN is used to regress the coefficients of 3D face model to reconstruct the virtual 3D face. In addition to the basic 3D shape and the textures, these coefficients also control the expression, height pose, and illuminations of the reconstructed virtual 3D face. Accurate reconstruction for the eye region means that the 3D gaze direction in the reconstructed virtual face must be consistent with the 2D gaze direction in the input image. However, the coarse-grained reconstructed image has a significantly projection error in gaze direction compared to the input image. Given an intuition hypothesis that the eye region projection of 3D virtual face, which returns correct eye gaze information, should be as identical as possible to the input image. Therefore, our goal is to complete the fine-grained construction of the 3D virtual face by replacing the texture of the eye region of the virtual 3D face with the precise texture of the input image. However, we found the coarse-grained 3D virtual face often produce a significantly shape projection error during aligning texture. In this paper, we propose a self-supervised learning algorithm to optimize the 3D parameters of virtual face to achieve the shape adjustment. After shape adjustment, points in the eye regions of the fine-grained virtual 3D face are strictly aligned with the pixels in the eye regions of the input image. Subsequently, we further achieve the better eye region alignment with the texture alignment. Specifically, we perform the eye texture alignment by using RGB values of the eye regions pixels from the input image to replace the corresponding texture values in the eye regions of the fine-grained virtual 3D face. To perform eye gaze information for the VR sense, we propose two key technologies through the 3D face rotation, which is guided by eye contact. Specifically, we first propose the eye contact discriminator to calculate the gradient of the 3D face as a guide for rotation. And second, we design a gradient searching algorithm to find the optimal rotation angle. The discriminator takes the 2D projection of virtual 3D face before and after rotation as input and outputs the direction of this rotation. For the training of eye contact discriminator, we construct the training side by rotation the virtual 3D face with different angles. Finally, we propose the gradient searching algorithm to find the optimal rotation angle in the optimization space. In the searching progress, we found the best point along the right path from the starting point based on the gradient opened by the eye contact discriminator. The eye contact discriminator provides us the gradient of virtual 3D face rotated in the in the h and vertical direction. Therefore, we can rotate the virtual 3D face h and v to search for the rotation angle close to the direction of eye contact. The optimization space is a loss distribution calculated by gradient, which is obtained from the eye contact discriminator in different directions. The yellow star represents the best point that can perform eye contact. The blue triangle indicates the starting point of the search. For each rotation, we use the eye contact discriminator to select the direction that is the fast way to the best point. We choose the direction with the lowest gradient among the four directions: up, down, left, and right. So we can say that. When gradients in all four directions are greater than 0, the rotation angle reaches the nearest neighbor points of the eye contact, and we further perform refinement for precise eye contact. To investigate the performance of the proposed automatic 3D virtual face rotation method, we perform a human evaluation to compare our automatic method with the manual rotation method. We built a special interaction system where users could accomplish eye contact by dragging and rotating the 3D virtual face obtained from our face reconstruction model in the center of the interface with the mouse. In the system, we can see that A shows the original import image. B is the preview of the gaze direction. C is the interactive 3D face model, which is reconstructed by our method. D shows the detailed information. In our setting, 10 people are asked to perform eye contact of 15 images, which is random selected from the ETH X-gaze dataset. The experiment results show that our method outperforms all papers for gaze direction from 21.65 to 8.01 in angular error and 1,200 seconds to 1 second in speed. In this paper, we first perform precise eye region reconstruction through joint optimization on 3D face, eye shape, and texture. Then we design an automatic face rotation algorithm to extract the accurate eye information, eye contact, and gaze direction. Quantitative and quantitative evaluations demonstrate that the proposed face reconstruction module can reconstruct 3D virtual face with precise eye gaze information. In addition, the novel 3D virtual face rotation module can realize the eye contact and further obtain gaze direction. In the future, 3D face reconstructions with eye gaze information from a single image or video show the potential usage in VR system and pave the way for the connection between the virtual reality and the real world. Thank you.
Okay, thanks, Jiadong. So let's start the third one. The third one is interactive mixed reality rendering on holographic pyramid. The speaker is Danqing.
Okay, I share my screen. Can you see that?
Yes, no problem.
Okay. Hello everyone, I'm Danqing from Beihang University, Beijing, China. Our paper is Interactive Mixed Reality Rendering a Holographic Pyramid. This work is together with Xuehuai, Lili, Wang, and Xiangyu from Beihang University. The motivation of our approach is to render glossy and specular reflection effects on holographic pyramid interactive with real audience and environment to achieve more realistic results. Render objects on the holographic pyramid that reflect the glossy and specular reflections of the surrounding scene. This imager is a previous work with indirect elimination in MR system, which cannot achieve glossy and specular effect, and the fidelity is not high enough. And this previous work renders color bleeding and high glossy effect for object in MR, which cannot render specular effect. So the challenge is to render specular and glossy objects efficiently in MR. We have proposed an interactive mixed reality rendering method on our holographic pyramid system. This is the pipeline of our method. The first step is acquisition and processing of environmental information. The second step is the generation of foreground point clouds. The third step is calculating foreground reflections by efficient retracing method. The fourth step is background reflection rendering. And the fifth is rendering result composition. Step 1 is real environment data acquisition. First, our system uses depth cameras to capture the dynamic foreground RGBD frame contained with the audience and the static background RGBD frame. Then, our system uses panorama camera to capture the background panorama. Step 2 is foreground point cloud generation. First, we use background subtraction algorithm to get foreground mask. Then, for adjacent frames, we use optic flow to get motion estimation. Finally, we generate the stable point cloud. In generating point cloud, we propose a pull-push-based temporal depth filtering algorithm, which makes the point cloud more stable and accurate. This is a combination of pixels in pore face. 4 pixels combined into 1. Each pixel holds depth and the confidence alpha of the pixel. In frame 0 to C-1, use temporal coherence of frames to update the probability distribution function of confidence and that of temporal depth difference. After frame C, use PDF alpha and PDF absolute D to predict depth and alpha. Finally, the depth with mean alpha is the combination value. Step 3 is efficient retracing for dynamic foreground reflections. First, we use quasi-blur to generate 2 MIP maps. Every level of MIP maps corresponds to the roughness of the metallic virtual objects. MMFG maps to the color of foreground point cloud. MMFM expands the border of foreground point cloud. After this, for foreground reflection, we voxelize the point cloud omega I and use voxel work algorithm to calculate intersections. For background reflection, we generate a cubic map based on theta and calculate intersections according to reflection rate. The first condition is ray EA, tracing to virtual object and reflecting on interior point cloud. The second is ray EB, tracing and reflection on the border of point cloud, and can get value on weight mask to achieve blind blur effect. The last condition is ray EC, tracing and reflecting on the background theta. We test our method with synthetic scene and real scenes, and this is our method's results. Here is the comparison results of our and the IBL method in 2 synthetic scenes. Compared to the ground truth generated with offline path tracing, The MSE of our method is 2 to 4 times smaller than IBL in all things. The visualization of MSE are shown. We compare our temporal depth filtering method with media filter and the TAA temporal filter in real things. The temporal MSE of our method is 129 to 212 times smaller than that of media filter, and 59 to 112 times smaller than TAA temporal filter. We compare the performance of our method and with IBL, and our method costs more for generating point cloud in step 2. And IBL costs more for projecting the foreground to cube map in step 4. Our method renders specular and glossy objects in real time. In conclusion, we have proposed an interactive rendering method on holographic pyramid and an efficient foreground point cloud generation method, and a real-time ray tracing method for glossy and specular effect. One limitation is that the depth of expanded point cloud is uniformly set with the average depth of edge. Another is that our method cannot support transparent materials. So in future work, we will improve our method to generate adaptive depths for expanded point cloud and expand our method to support transparent materials. Thank you for your attention.
Okay, thanks to Danqing. And the first paper is rectangular mapping-based foveated rendering. The speaker is Jiannan from the DA Lab, Shanghai Jiaotong University. Jiannan, please.
Okay, can everyone see me?
Yes. Yes.
Okay, so let's begin. Hello, everyone. I'm Jiannan Ye from Shanghai Jiaotong University. It is a great honor to present our paper, rectangular mapping-based foveated rendering on behalf of all 6 authors. Nowadays, VR rendering requires very high resolution frame rate and visual quality, which is computational demanding. So acceleration is becoming more critical. Foveated rendering addresses this challenge by rendering with a non-uniform resolution, which renders the vivo region with higher quality and the peripheral with lower quality. There is much related work about foveated rendering, and most of it discuss how resolution or sampling rate varies across the visual field. First is hyperbolic model, which models the reciprocal of accuracy as a function of the eccentricity. But in implementation, the vivo region must be rendered for 3 times, and the larger outer layer is unnecessarily rendered. Linear model introduces a linear sampling rate fall-off into ray tracing, but it is not usually suitable for rasterization. In polar space model, foveation is achieved by mapping an image forth and back between the Cartesian and the polar space, but there exists a curved artifact during the transformation. Now let's talk about our approach. Different from traditional deferred rendering, our 2-pass pipeline applies a rectangular mapping to the geometry buffer and saves the metadata into a transformed G buffer in smaller size. Then we calculate the lighting, and then finally we apply the inverse mapping to get the foveated result. Doing lighting with a smaller G buffer is where we can reduce the cost. For pixel distribution, we are motivated by the nonlinear optical length equation describing the relationship between the object distance and the image distance. As demonstrated in this figure, the original uniform samples located at DO can be transformed into the samples at DI. The specific distribution of DI is related to the F value. Let's look at an image example. Using the equations earlier, we can transform the image back and forth according to the pixel position. A normal image can be mapped into a small warped one, where more space is used stores FIFO information and then map back to get the non-uniform quality. We can easily find that in 2 dimensions, mapping along x and y-axis can be considered separately. There are 3 main advantages of our method. First is decoupling. As shown in this figure, regions with more vertical patterns are sensitive to the compression along the x-axis. By decoupling the 2 directions, our method is able to adjust the level of compression for each axis independently. So we can get a better overall quality depending on the image content by better distribution of pixels. Or in other words, we can say our method has the potential to get more compression. We can find the same fact in rendered image as shown in this figure. Peripheral regions with more compression in x-axis, in y-axis looks better than the ones with more compression in x-axis. We say it has X preference for better quality, which can only be achieved on our decoupling. The second advantage is that our method is robust in aliasing. As shown in this figure, the curved pixel mapping of log polo foveated rendering KFR lead to curved artifacts in most patterns. Then our method utilizes the middle buffer completely, which KFR can't. We did several user studies in VR to profile our method. The basic procedure is shown on the right. We ask the participant to compare the foveated rendering with the full resolution rendering and evaluate the quality. In user study 1, we tested the result with different combination of fx and fy to estimate the optimal distribution parameter. We found a similarity and a consensus among most participants and choose fx and fy with the highest score as the best parameter for later use. In user study 2, we tested the foveated rendering with different compression parameters, sigma, to estimate the biggest sigma with acceptable image quality. We set a score threshold of 2 and find 2.6 as a possible largest sigma, at which the users consider the quality only marginally different from the ground truth. We compare our method with 3 other methods. To conduct an apple-to-apple comparison, we choose a parameter to fix the theoretical speed up across all methods. We conduct a 2 AFC experiment to compare IMFR method with others. We observed close to random gains when comparing with reference, and our method is statistically more preferred against all other methods. For quantitative evaluation, we evaluate the average image quality of the frames using 4 metrics. The results are shown here. Compared to other methods, our proposed method, IMFR, generally provides the best render quality. For visual results, the IMFR renders the FIFO region with good visual quality and preserves the better quality for the peripheral regions. The result is similar in this image. IMFR with sigma equals 2.6 reduce the frame time by 45% and achieves the speed up of 1.8 times. The limitation and future work are shown here. There is a gap between the subjectively and objectively estimated parameter, which we have to mitigate. And it also leaves the automatic parameter estimation as an important future work. As a summary, we present rectangular mapping-based foveated rendering, which outperforms the state of art in visual quality while maintaining minimal rendering cost, and which is easy to integrate. Thank you. We thank all reviewers for their great advice, and thank you for listening.
Okay, thanks to Jiannan, and that's a great job. And now we started the 5th paper, dynamic projection mapping for robust sphere posture tracking using a uniform biased circumferential markers. The speaker is Yuri from the Yuri, please.
Yes, I prepared for it. Thank you for your introduction. Again, my name is Yuri Mikawa from the University of Tokyo. I'm a currently PhD course student, and yeah, here I start my presenting my TBCG paper. Reality named SAR. Recent trend of SAR is presenting the real-time motion information in the space directly. It is thought to be useful to enhance the sport's ability. For example, previously, as shown in the left side, the golf swing is enlarged by projecting on the floor, which makes the practice easier. As shown in the right side, the other research shows the estimated orientation of the ball as a floating image by a HoloLens. As well as previous researches, we focused on the sports motion visualization. And as you know, most sports use balls, and then projecting graphics onto the ball surface is thought to be effective. Here, the precise ball tracking in the dynamic and complex situation is required. For example, in the sports situation, multiple players often hold the ball by one or more hands, and sometimes the whole ball body is occluded by the human body. So we think about the usage of markers for the ball tracking because the ball is a rotationally symmetrical body and therefore requires the markers for the posture detection. Furthermore, fast tracking is effectively achieved by the usage of markers rather than markerless method. However, previously, there is a trade-off between the initial construction of the object orientation. We need to think about the new design of tracking markers. Please wait. Then we propose the marker of circle-like shape, called circumferential markers. Originally, the circle shape is robust against the blurring so that widely tracking and projection is enabled. And since the circle shape indicates its orientation geometrically, the initial construction of the ball orientation is enabled with the appropriate algorithms. Focusing on these features, we proposed two types of circumferential markers. One is uniform and the other is biased. And they are called uniform circumferential markers as UCM and biased circumferential markers as BCM. The three basic performances common between them. First, automatic construction of initial pose is enabled. And second, it is strong against occlusion. Third, the tracking range in the depth direction is so large. Only for the biased circumferential markers called BCMs, the absolute posture tracking can be achieved. So I show these demo movies, and you can see this projection appearance using our markers. It can visualize the rotation value and the direction onto the ball directly. And as shown in the left side, it enables wide projection onto the ball from the front to the back. As shown in the right side, rhythmic gymnastics also collaborated with our marker-based projected sphere. And yes, the first impression of this is so beautiful, I think. You can watch this movie on YouTube using this QR code, and don't worry, I show this code again. Therefore, our paper newly presents a biased circumferential markers BCM in the right side. And therefore, I introduce this function and the performance. Please understand that here the outline of the method will be explained because the presentation time is limited. The BCMs have the coding for the absolute posture estimation, and it is made from the directional and radius combination of the adjacent markers. For example, the inner circle are put uniformly as well as UCM and used for the continuous tracking. On the other hand, the outer circle indicates the Unicode ID by, for example, shifting its position against the inner circle and varying its radius. The combination of these features of the adjacent markers can express the Unicode ID, for example, this one and this one. And this design enables the initial construction of the absolute orientation of the ball because each ID is unique. And I will demonstrate the appropriate number of the combination and design in our paper, so please refer to it for the detailed information. Furthermore, it should be noted that the area where the outer circle can be shifted is so narrow, and bad placement of these markers easily causes misidentification, and it is a difficult problem. And at the same time, we need to vary the placement of outer circle for the easy identification. Therefore, we made design rules that should be kept. For example, stick parts use the latch of the limited area, so they should not face each other. And because the cut part of the circumference easily causes misidentification, so the narrow part of the circumference should not be too narrow. For the time limitation, please refer to our paper for the detailed tracking algorithms and formulated design rules. Not only the marker design, but also the projection system is newly proposed. It is newly combined with coaxial infrared light as shown is this one. This is an important system to realize high-speed sticky projection mapping onto the sphere, even in the wide space. And I use this system for the evaluation and demonstration. Here is the evaluation system. We compared our proposed circumferential markers as UCM and BCM to the two previous typical markers, dot markers and EDCMs. As you know, the dot marker has the most basic shape, and it just uses the dots, but cannot realize the initial construction of the board posture because this marker shape doesn't indicate any geometrical information. On the other hand, the EDCM was proposed by Watanabe et al., and which expresses the Unicode ID by the cluster marker and enables the posture identification. However, the complex shape is weak against the blurs, so therefore it is also weak against white motion. So here is the evaluation flow. I show this video, and we use the turntable which rotates at the constant speed. And the basic tracking performance is evaluated as the same high quality. And the next, I use a hand model for the partial occlusion. It is a complex occlusion, and we evaluated this. As for example, dot marker and EDCM can lost easily because marker number is so low, but UCM and BCM can continue tracking, but BCM has vibration, but it can continue the tracking. And after that, overall occlusion is conducted using the cardboard. And after occluded, the dot marker cannot continue the tracking, but UCM, BCM can continue it. But the UCM recovers its the relative posture. And I evaluated the lateral motion in XY direction, and it shows the same performance. And after that, I also evaluated the motion in the depth direction. And as you know, the EDCM cannot continue the tracking because it is so weak against the blurs. Sorry. So there is here is the conclusion. Two types of circumferential markers are proposed, and their performance are evaluated confidentially. And the demonstration also shows the strong evidence for the actual implementation. Please watch our YouTube using this code. Thank you for listening to my presentation.
Thanks, Yuri. Very impressive results. So, okay. Okay.
Yeah, please search our paper in YouTube, the Value Light 2, and you can watch this video too.
Of course. Okay. Let's start the sixth one, and dynamic multi-projection mapping based on parallel intensity control. The speaker is Yoshihiro Watanabe. Yoshihiro is from Tokyo Institute of Technology. This paper is from the journal track, TVCG journal track of the ISMA of the IEEE VR this year. Please.
Hey, can you see my screen and can you hear my voice?
Yes.
Okay, thank you. Thank you for introduction. I'm Watanabe. So today I would like to talk about dynamic multi-projection mapping based on parallel intensity control. And dynamic projection mapping requires several millisecond latency from the motion to projection to avoid the perceived misalignment between the projected image and its target. Recent work shows it is possible. However, some of the remaining challenges in dynamic projection mapping are extending the mapping areas and removing shadows due to the single projector configuration as shown in this video. A simple and effective solution to this problem is to arrange multiple projectors around a thing and control them simultaneously. The main issue in multi-projection mapping is determining which projector illuminates the points on the target surface and how high the intensities must be. Two methods are proposed to avoid the artifact in the overlapping projected areas. The blending method can run at high speed. However, this method can work only in the limited conditions. The global optimization method formulates the intensity control more accurately by using the surface geometry information and light transport model. However, unfortunately, this calculation speed is very slow. In addition, the computational complexity of this approach increases quadratically with an increase in the number of projectors. In addition, in the related work, the number of projected targets is limited to 1. Therefore, adaptive shadow removal between multiple targets in a dynamic scene is not demonstrated. So in this study, we present a method to calculate the projected intensities in parallel for each pixel of each projector and a new networked dynamic multi-projection mapping system. We demonstrate multi-projection based on drastically low latency using a system comprising a network of 4 high-speed projectors. Okay, let me describe our method briefly at first and its advantages later. The goal is to realize a particular illuminance, EHC, at each surface point. To realize this, our method calculates the luminance intensity IHZC for each pixel for each projector in parallel. So the key is the geometry-aware weight. This geometry-aware weight contributes to realizing the high-resolution multi-projection mapping. Our method also effectively hides the miscalibration. Our method also ensures that the weight varies smoothly on the surface by using the exponential term k. However, in the parallel calculation, this weight calculation causes errors. The problem is that the projected pixels spread on the surface and they can overlap with pixels from other projectors. Therefore, the luminance intensities for all related overlapping pixels must be determined simultaneously. This solution conventionally results in global optimization. On the other hand, our calculation leverages the insight that the projected pixels from different projectors in overlapping areas can be approximated independently if the pixel sufficiently small relative to the surface structure. So please refer to our paper more details. Our method can be implemented using ray tracing. This ray tracing-based implementation can accelerate the calculations such as visibility check without redundant calculation of multiple images. Thanks to the parallel calculation for each pixel of each projector, our method allows a distributed system configuration such that the number of projectors can be increased to form a network for high scalability. This configuration is also effective for dynamic projection mapping because this application needs from 500 to 1000 frames per second high-speed projector requiring wide transfer bandwidths. Okay, so this graph shows the image generation time. The time in yellow represents a pixel parallel intensity control. The times in orange and blue are required to render a single projected image and transfer the image respectively. So we found that the increase in intensity control time was small as the number of projectors increased. By adding the tracking and the projection, the total latency for 4 projector configuration was 9.5 milliseconds, and this performance is limited by the user consumer tracking device. This slide shows the comparison. The goal of this mapping was to ensure that the target surface has the same white luminance. The slightly different areas are found only in the white dashed boxes. Consequently, it was confirmed that our method could achieve quality in the appearance similar to that of conventional global optimization method while improving the calculation speed. Let me show the demonstrations using 4 8-bit high-speed projectors. We confirmed that the projection range is expanded using 4 high-speed projectors. Even when the object moves, the shadows due to the occlusion are compensated in real time at a high speed. Based on the newly developed color mulch projection, in this case, we use the 2 color projectors. Our method can work even on a non-uniform albedo surface. We can compensate the textures. Of course, the colorful textures can be mapped onto the moving object. And in this scene, we produce the grass bunny by projection mapping. In this mulch projection in dynamic scenes at a practical speed is confirmed to have a strong impact on enhancing the reproduced reality. Okay, the video through the Zoom may not be played in good quality. So if you have time, please visit our website to check the video in better conditions. Okay, this is all for my presentation. Thank you so much for your kind attention.
Okay, thanks. The video is very good.
Thank you, thank you.
So we have 5 or 10 to 10 minutes to do the Q&A. I didn't see any questions from the Google Docs, so I will ask some questions. And the first one for the usual hero, and I noticed in your video, the rendering is always in the dark, very dark place, and the background is dark. But when you capture the video, I think the environment is more brighter. And so, what's the condition of the lighting when you capture, and what light condition when you rendering? So, is any relations between the capture and the rendering for the lighting relation?
Okay, thank you.
Lighting condition, yeah.
Okay, thank you. So in this system, we assume that the environmental lighting is turned off because if the environmental lighting illuminates the target surface and this lighting is overlapped with the projection mapping projection, then the contrast becomes very low. So the environmental writing should be smaller, or environmental writing should avoid the target surface. So I think in future, we successfully developed this kind of multi-projection system. So we maybe use this kind of projector as a environmental writing, which can avoid the target surface, but can illuminate the other surfaces. I think that's the future work, I think. But anyway, for the rendering assumes that our target surface is only illuminated by the projection mapping image through the projector. That's my answer. Thank you.
Okay, thank you. So for the rendering result, we just want to show our intensity control better. So we make all the other light dark and just keep the intensity control result, right?
Yes.
Okay.
Thank you.
Thank you. So let me check again. No. So the second question is for the first paper, rectangular mapping based foveated rendering. Jiannan.
Hi, I'm here.
So the question is, what's the size of the render of the foveated region? Because I noticed you got a very fast performance. So I want to know what's the size of the foveated region you rendered. Yeah.
Okay, different from traditional foveated rendering, which has a FIFO region for certain eccentricity. Here we apply a global transformation method, which we didn't define a specific region, which means that we are like the pixel density is gradually decreased from the center to the peripheral, and we can see that if the pixel density is above 1, which is the original resolution, we can say it keeps the resolution at the original, and inside the conversion, we didn't calculate the certain eccentricity of the FOVO region, but it is generally a little smaller than the traditional method, like the foveated 3D graphics, which determine like 10 or 5 degree of eccentricity. Here we have a smaller eccentricity for the FIFO region, because we theoretically distribute more pixels to the peripheral region to keep the overall quality more satisfying.
Okay, thanks. Very clear. Okay, the third question is for the Yuri, the fifth paper, and I noticed your result is very robust for the sphere posture. I want to know what's the challenge if we extend this method, this marker to the maybe some other shape.
American football or the baseball, this club, for example, I think about yes.
I mean cube, maybe a cube, a cube, other shape, maybe a marker, maybe a cup. Is that okay or not?
It's difficult question. I cannot answer yes or no because I haven't searched it in the detail. I firstly used the sphere because its cut shape is definitely circle, so we can put the circle marker easily onto the sphere. On the other face shapes like the cubes, it cannot be put the circular shape onto the cube, so it's difficult. We need to deform such shapes into the another shape, I think, another marker shape.
Okay, not easy.
Yes, okay. I think the line shape is okay, but the circle is not, I think.
Okay, thank you.
And thank you for your question.
The last question is for the third paper, Danqing. So now the method is Danqing, are you here?
Yes.
Okay.
I'm here.
Now the method works for the spicular and the glossy object and the diffused object. So now I think it cannot work on the translucent or transparent object. So do you have some ideas make this method for the works for the more materials?
I think this is our future work. We think that we can change for our method is one bounce ray tracing, and now we use so we need to change our ray tracing method with multi-bounce, and we should change the optimism algorithm to optimize our method. Our multi-bounce ray tracing method, and for our point cloud model. So we need to change the optimism algorithm. Another is we can introduce photon mapping method to our point cloud models to achieve transparent effect or the cosmetics effect. I think this two method is our future work, our future work. That's all.
Okay. Let me check the online. Okay, we have a question. We have a question for the last paper. And thank you, the impressive work. Maybe I missed it, but let me know how to integrate the occlusion-aware optimization into your distributed system. To my understanding, the occlusion part need to be treated as a global optimization.
Okay, thank you for question, Iwai-san. So that's the main issue we focus in this study. So first of all, we can detect which project can eliminate the point without occlusion based on the ray tracing efficiently. But if the point is eliminated more than 2 projectors, we need to decide their intensities simultaneously. That results in the global optimization conventionally. That's the point, I think. However, if the pixel resolution is greater than the spatial frequency of the surface structure, its smaller pixel yields the smaller surface areas, which can be considered as more planar. Therefore, we can simply consider the surface geometry on the point projected from the center of the pixel as a representative of the spread pixel area. In addition, if we can assume that the surface area overlapping with pixels from different projectors is a planar such surface patch, each pixel can approximate each pixel intensity of the other projector with small errors. So simply speaking, so each pixel can correctly estimate the other estimated intensity. That's the point. This assumption can enable the parallel calculation. The simple trick, but explanation in just orally is a little bit difficult. So if possible, let me talk later. Okay, thank you.
Okay, thanks. Thanks all the speakers again. Time goes by too fast, so we need to end our session. And thanks all the speakers, and thanks everyone to attend the rendering session of IEEE VR 2022. Thanks. That's all for rendering section. Thank you. Bye-bye.